Okay, so today we're looking at solving some more complex inequalities. The first couple examples are going to require some different cases be used to solve the inequalities. And then third, fourth, and fifth examples, we're going to be looking at some absolute value inequalities, which probably will be some review from your Algebra 2 course, okay? So let's go to example 1 here. And we have a simple inequality, 2x minus 3 to the negative first power is less than 1. Recall, whenever you have an exponent that's negative, you can turn it positive by putting it underneath 1, right? So this would be no different than saying 1 over 2x minus 3 is less than 1, right? Okay, now, what do you think we would want to do here to solve this inequality? What would be a good first step, given we have a fraction now? Yeah.
Multiply by 2x minus 3.
Multiply both sides by 2x minus 3, right? That would clear the fraction. But here's the thing. I don't know what x represents, right? So when I multiply both sides by 2x minus 3, I don't really know if I'm multiplying by a positive value or by a negative value. That matters in terms of having to flip our inequality symbol or not, right? So that's why I have this hint listed over here that we have to consider two different cases, okay? So let's call this first one case 1. We're going to say 1 over 2x minus 3 is less than 1, and we're going to say that the 2x minus 3 that we want to multiply by is a positive value, greater than 0. Okay? And then our second case, what we can do is let's just copy all of this again. Copy it. Paste it over here. And in the second case, all I'm going to do is change 2x minus 3 from being greater than 0 to being less than 0, meaning it's now negative. Okay? All right, let's solve case 1 here. I'm going to multiply both sides by 2x minus 3 like you suggested. And if 2x minus 3 is a positive value, I don't have to flip my inequality symbol when I do that, right? I'll end up with 1 is less than 2x minus 3. Let's finish solving that. 4 is less than 2x. Or 2 is less than x. And if it's helpful, you can flip that, right? You can say x is greater than 2. And then solve the other half of this. X will be greater than 3/2, right? Now, move that down. We need some more room here. Okay, now this is an and statement. So when we graph these on a number line, put the critical values, 3/2, 2. So greater than 2 looks like this. Greater than 3/2 looks like this. And is an intersection, an overlap, where both inequalities have to be true. That would occur at values larger than 2, right? So that would be the solution to this first case. All right, now we're going to solve the second case the same way. We're going to multiply both sides by 2x minus 3. But now 2x minus 3, being that it's negative, when we do this, we have to flip the inequality symbol, right? So these are going to wipe out. I've done that here too. And I'll make it now greater than 2x minus 3. 4 is greater than 2x. and then 2 is greater than x, or that's the same as saying x is less than 2. Over here, x is less than 3/2. So it's going to be the same two critical values. But when we graph these, they're now going in the other direction. X is less than 2, less than 3/2. And it's another and statement, so we're looking for the overlap, what they have in common. That would be any value less than 3/2, right? And now we take the results from case 1 and case 2. We find the union of those. We bring them together for our final solution set. So that's what I'll put on this given number line here. Let's go 0, 1, 2. So the first half was x greater than 2. The second half was x is less than 3/2. Here we are. And then here's your equivalent interval notation. Any questions on that example? So the takeaway from this should be, if we're working with an inequality to solve and we have to multiply both sides by an expression that includes a variable, we're probably going to need to use two cases like this to consider that variable could lead to us multiplying by a positive or by a negative, right? We have to consider both possibilities. Okay. All right, example 2, we start with a compound inequality. And I'm going to immediately break this up, separate it like so. Negative 2/3 is less than 1 over x, and 1 over x is less than 0, right? Okay, now let's focus on the left side. What do you think would be a good first step in solving this half of the inequality? Multiplying by x. That would clear the fraction over here, right? Or we could multiply by 3x, and it would actually clear both fractions, right? Now, if we're going to multiply by either x or 3x, we have to consider, well, what if that would be a positive value versus a negative value? So this seems like it could be a situation where we need two cases again, right? Well, look over here, though. If 1 over x is less than 0, what's true of x?
It's also less than 0.
X has to be less than 0, right? Okay. I plug any positive value in for x here. 1 divided by any positive number would not make a true statement. So I can immediately say here that x must be negative. Or x has to be less than 0, right? Okay, so we come back to here on the left side now, and we can say, well, if I'm going to multiply by 3x on both sides, if x has to be negative, isn't 3x going to be negative? So we're multiplying both sides by a negative value then, which means we're going to have to flip our inequality symbol. Okay, these 3's are going to wipe out. These x's are going to wipe out. You're going to be left with negative 2x is greater than 3. And x is, we got to divide by a negative again, right? So we actually got to flip it back. So we flipped the first time when we multiplied by 3x, since it represents a negative, and then we flipped again when we divided by the negative 2 here. Okay? Now notice this is a and statement. So we have x less than negative 3 halves and x is less than 0. If we were to graph those, let's label down here, 0, negative 1, negative 2. So less than 0, less than negative 3 halves. Where are they both true? Any value less than negative 3 halves, right? Okay, now I'll tell you the reason this kind of worked out as nicely as it did is because the second half of the inequality, it was a 0 there. That's what allowed us to be able to reason out right away, just using some number sense, that for 1 over x to be less than 0, x has to be less than 0 itself, right? If that were any other number than 0, we wouldn't necessarily always be able to make, that conclusion. Okay. All right. Example 3. Now we've got an absolute value inequality here. You guys cover absolute value inequalities in Algebra 2. I feel like there we don't really always learn it conceptually. We just procedurally learn it, but don't really get it. The goal today is conceptually understand this, okay? So what does it mean to find the absolute value of a number? Yeah. Go ahead.
Oh, to find the distance from 0?
To find the distance from 0 on the number line, right? The absolute value of number is its distance from 0 on the number line. Okay, so I want the absolute value of 2x minus 2 here to be greater than or equal to 4. So let's focus on the 4 right now. Let's try to draw a picture to visualize this. Put 0 in the middle. So I want all numbers on the number line whose distance is 4 or more from 0. Well, you're exactly 4 units from 0 at 4 itself, right? And where else?
Negative 4.
Negative 4. Okay. And then where else would you be greater than 4 units from 0?
To the right of the number line of 4 and to the left of negative 4.
Very good. To the right of positive 4 and to the left of negative 4, right? Okay, so what we've got to realize is here's where we now bring the 2x minus 2 into play. That 2x minus 2 has to be greater than or equal to 4 or less than or equal to negative 4. So we're going to write this as a or statement. Okay, now solve each one of those individually. 2x is less than or equal to negative 2. X is less than or equal to negative 1. Carry that or down. 2x is greater than or equal to 6, and x is greater than or equal to 3. And this should be a typical or statement when you graph it. Less than or equal to negative 1, greater than or equal to 3 for your final solution. And of course, here's your interval, negative infinity to negative 1 inclusive, union 3 inclusive to infinity. Questions there?
Mr. Mosher.
Yes.
On like a test,
Mhm.
is it gonna matter if we have to put a citation or interval notation? Like, will it ask
I will tell you which notation to use, yeah. More often than not, I'm going to ask for interval like I did on the homework last night.
All right.
I personally prefer interval. It's less writing usually.
Yep.
Yeah. Okay, example 4 next. So we have another absolute value inequality. This one's a little more sophisticated. First thing we got to do here is we got to isolate the absolute value, meaning get it by itself. Okay, now the one thing you're not going to do ever, you're not going to try to distribute this 3 into the absolute value. There is no distributive property that works across absolute value, okay? Instead, we're going to add this 9 over. And then what would we do with that 3 at this point if we're not allowed to distribute it? Divide it, yeah. Okay, so that'll lead me to the absolute value of 2x plus 6 is less than 8. Now the absolute value is isolated, and I'm going to use some conceptual understanding on this about absolute value. I want all numbers for 2x plus 6 whose distance is fewer than 8 units from 0. So let's visualize this again on the number line. Here's 0. Here's 8. Here's negative 8. We're exactly 8 units from 0 at those two numbers, right? But now we want to be less than 8 units from 0. So where on the number line does that place me? In between those values this time. Okay, so this is an intersection that we're dealing with, right? Okay, so this 2x plus 6 has to be now between the negative 8 and the 8. We'll make a compound inequality out of it. Let's move that away. So we'll subtract 6. Negative 14 is less than 2x, which is less than 2. Divide your 2 out. Need more room. We're going to be between negative 7 and 1. And we don't want to include those values this time, right? Questions on that example? So you will find that all absolute value inequalities can be written as a compound inequality, either as a or statement or an and statement. Okay. Now, example 5, we got a couple special cases to consider. And this will be quick. Let's say I want the absolute value of a number to be greater than negative 3. So reason that out. What's it asking for? It wants all numbers whose distance from 0 is greater than negative 3 units. What numbers would make that true? I want all numbers whose distance from 0 is greater than negative 3 units. That would be all real numbers, wouldn't it? Every number in the entire number system is going to have a distance that's greater than a negative, right? So that's a simple one to solve. Absolute value of x is less than negative 3. All numbers whose distance is fewer than negative 3 units. Not possible, no solution, right? The empty set. Think, every number that I place in for x here, when I take the absolute value of it, it's going to result in a positive number, right? Because it's a distance. And a positive number will always be, or will never be less than a negative, okay? All right, so you can make these conclusions once the absolute value's been isolated and you still have a negative on the other side, okay? Very good.